Welcome back to another deep dive. We're really thrilled to have you with us today.
Yeah, it's going to be a good one.
It really is. So, as part of our ongoing mission to share state-of-the-art foundational generative AI papers with you, today we are looking at something just truly mind-bending.
Absolutely mind-bending.
We're exploring how artificial intelligence learns to, dream or, I guess, predict the future in these highly unpredictable real-world scenarios.
Which is fundamentally changing how we look at AI safety.
Right, exactly. And the source for this deep dive is a really fascinating paper. It's dated June 30th, 2026, and it's titled Flow Matching in Feature Space for Stochastic World Modeling.
Quite the mouthful, but the concepts are incredible.
Yeah, for sure. It comes from a team of researchers, Francois Porcher, Nicholas Carrion, Kartik Alahari, and Shizhe Chen, and they're hailing from FAIR at Meta and Inlaria.
It's just a critical piece of research because, if we ever want autonomous systems to actually function safely around us, they need to fundamentally change how they perceive time.
Yeah, and the reason you should care about this, whether you're, fascinated by the tech behind autonomous driving or you're just insanely curious about how AI maps out reality, is that understanding how a machine handles the uncertainty of tomorrow, it completely changes how we view AI capability.
It really does. It's about dealing with the unknown.
Right. Think about it. You know when you're driving down a suburban street and you see a squirrel dart out to the very edge of the road? There's this split second where your brain just sort of branches.
Yeah, in a fraction of a second, your mind is simulating multiple parallel universes.
Exactly. Universe A, the squirrel freezes. Universe B, it kamikazes right under your front tire.
Nightmare.
Total nightmare. And then Universe C, it just runs back up the oak tree. Your brain effortlessly holds all three possibilities at once without mixing them up into some, I don't know, weird mutated mega squirrel.
Right, they stay distinct.
Yeah, and it's the difference between you safely navigating a crosswalk and making a catastrophic miscalculation. Okay, let's unpack this. What is the core problem the researchers are trying to solve when they try to put that same biological trick into a machine?
Well, the core problem is what we call world modeling. So an AI needs to look at past context, say, the last few frames of a video from a car's dashboard camera, and predict future states.
Okay, sounds simple enough.
You'd think so, but to do this effectively in the real world, the AI is basically burdened with two simultaneous tasks that are, well, they're fundamentally at odds with each other.
Oh, so?
First, it has to predict an uncertain branching future, just like your squirrel example. The future isn't a single track, It's a tree of possibilities.
Right.
But second, it has to preserve incredibly high-level semantic details. It needs to know the exact 3D geometry of a pedestrian, the physical boundaries of a vehicle, the precise depth of the scene.
Because if it doesn't know those physical boundaries, it can't drive.
Exactly. If it loses that structural detail, a self-driving car can't actually plan a path to avoid an obstacle.
So, reading through the paper, it seems like current systems essentially force a compromise here. Like, you either get an AI that can imagine multiple futures but goes kind of blind to the physical structure of the world, or you get an AI with perfect vision that is stubbornly forced to only imagine one strict future.
Yeah, that's exactly the compromise. And we can break down why that happens. Let's look at the first approach, which involves VAE-based stochastic models. 2.2 is a good example.
And VAE stands for variational autoencoder, right?
Correct. Now, these models are actually quite good at imagining multiple possible futures, so they handle the branching universe as well.
But there's a catch.
A huge catch. To make the intense math of generating futures computationally feasible, VAEs work by compressing the massive amount of video data into very low-dimensional latent spaces.
Ah.
They take all that rich visual data and squeeze it through a bottleneck, optimizing purely for the ability to reconstruct pretty recognizable pixels on the other side.
Which creates what we could call the pixel trap.
I love that term, the pixel trap. Because when you compress the data that severely just to optimize for pixel colors, you destroy the fine-grained semantic structure.
So it looks nice to a human, but it's useless to a computer.
Exactly. The AI might generate a visually pretty picture of a street, but it loses the rigid geometry needed for dense perception tasks. A downstream safety system trying to accurately track the 3D bounding box of a moving car is suddenly flying blind because the underlying structural detail was squeezed out during the compression. The semantic integrity is just gone.
Wow. Okay, so if compressing the data ruins the semantic detail, the natural fix is to just skip the bottleneck, right? Like use strong, high-dimensional representations.
That's the logical next step, yeah.
And the researchers highlight using pre-trained features from a model called DNOv3. From what I gather, DynoV3 is a self-supervised vision transformer that doesn't just look at pixel colors, but it deeply understands scene geometry and object boundaries, all without needing human labels.
It does. It provides incredibly robust, highly structured data. Which brings us to the second approach, the deterministic predictors, like DynoWM.
Okay, deterministic.
Yeah, these models utilize those rich, high-dimensional DynoV3 features. The AI maintains a near-perfect semantic understanding of the scene's geometry.
But you said deterministic. That sounds like a flaw.
It is the fatal flaw here. These models are mathematically constrained by their architecture to output only one single prediction for the future.
Which is a massive problem when the future is inherently unpredictable. I mean, if an autonomous car sees a vehicle ahead that might either slam on the brakes or speed up to make a yellow light, a deterministic model just panics, doesn't it?
It does. It doesn't know how to handle the fork in the road.
It's like it looks at the two possibilities, tries to minimize its mathematical error, and predicts the absolute average of those two futures.
Exactly.
It's like asking a friend if they want to order pizza or sushi for dinner, and they compromise by ordering you a pizza topped with raw fish.
Right. Nobody wants that.
No. They averaged the two valid options, but the result is a completely useless, impossible reality. It basically creates a blurry mean that corresponds to no valid future at all.
And that pizza sushi monstrosity is actually backed up by a formal mathematical proof in the paper.
Really? They proved the raw fish pizza.
Well, not with pizza, but yes. When you train a deterministic predictor, you typically use standard L1 or L2 regression losses. Think of these as like penalty systems.
Okay.
The model is penalized based on how far its guess is from the actual outcome. So in a branching universe where a car might brake or accelerate, being wrong in either direction carries a heavy penalty.
So the math fundamentally forces the model to hedge its bets.
Precisely. It collapses multimodal futures into a single point estimate, calculating the conditional mean or median just to minimize that penalty.
Wow.
So the mathematical average of a car braking and a car accelerating is a blurry ghost car hovering somewhere in between. It is functionally useless for a downstream planning system that needs to know where the physical bumper of the car will actually be.
That's terrifying. So we are stuck. Compressing data into VAEs loses the crucial semantic detail because of the bottleneck, and averaging high-dimensional data in deterministic models creates impossible ghost futures because of the math penalties.
You've got it.
So the obvious question is, how do we get the best of both worlds?
And this leads directly to the researchers' solution, which they call FlowWM. They asked a really fundamental question. They said, what if we run a stochastic generative model, one fully capable of imagining multiple distinct futures directly inside that incredibly rich, high-dimensional pre-trained feature space of DNOv3?
So high-dimensional dreaming.
Exactly.
But how does the AI actually generate that dream without compressing it first? I mean, how does it handle the data?
They use a technique called flow matching, and they do it directly within this massive feature space. Instead of compressing the world down to something tiny, like 16 dimensions, to do the math, they keep the world in its robust 384-dimensional per-patch glory.
384 dimensions.
Yeah, per patch. Flow matching is essentially about teaching the model to chart a path. Imagine a complete field of static noise. The model learns the velocity vectors, the currents, if you will, required to smoothly push and map that static noise into a valid, highly detailed future state of DynoV3 features.
So it learns to draw the map from chaos to structured reality.
Beautifully put, yes.
Wait, I got to push back here, though. 384 dimensions per patch is a colossal amount of data.
It is massive.
Right. So if you're running a generative flow model in a space that massive, doesn't it just completely bog down the computation? I mean, standard diffusion models are finicky enough in low dimensions. How do the researchers keep this from becoming just a sprawling, untrainable mess of numbers?
It was definitely the most significant hurdle they faced, because previous attempts to just copy-paste standard diffusion recipes like the standard diffusion transformer or DIP architecture used in VAEs, they failed or became highly unstable in these massive spaces.
Because the sheer volume of variables just overwhelms the network.
Exactly. So to fix this, the researchers introduced two massive architectural design choices to FlowWM. First, they implemented what they call a wide projection head. They set the internal projection dimension to 1024.
Wait, 1024. So they deliberately made the hidden dimension inside the neural network much larger than the 384-dimensional latent space it is actively trying to manipulate.
They did.
That seems totally counterintuitive. Usually you want to streamline things, right?
You might think so, but they found that ensuring the hidden dimension significantly exceeds the per-catch latent dimension is absolutely critical. It's the only way for the model to accurately predict those complex velocity fields in high dimensions.
Okay, I think I see.
Think of it as giving the model a massive mental scratch pad. If the internal processing head is too narrow, it acts like a cognitive bottleneck. The model simply doesn't have enough internal bandwidth to calculate all the moving parts and its performance tanks.
Oh, so the wide head just gives it the necessary computational breathing room.
Yeah.
Okay, that makes sense. Give the math enough room to stretch its legs. So what was the second fix for this high-dimensional problem?
The second fix is a resolution-dependent time-step shift.
What does that mean?
Well, in diffusion and flow matching, the model learns by gradually removing noise over a series of sequential time steps. When you scale up the dimensions of the data you are working with, you inherently increase the sheer volume of noise the model has to deal with at the very beginning of the process.
Right, bigger space, more noise.
Yeah, and if it treats all time steps equally, it just gets bogged down. So they applied a mathematical shift that rescales the diffusion time. It purposefully skews the training distribution toward the noisier, earlier time steps.
Oh, I see. So by doing that, they are basically forcing the model to spend the vast majority of its training energy wrangling that massive initial wall of noise rather than obsessing over the tiny final details at the end of the generation process.
That is exactly the mechanism. It stabilizes the whole flow process because the network learns to confidently handle the hardest part, the high-dimensional chaos, before worrying about the fine-tuning.
Okay, so they've built the architecture with wide heads and shifted schedules to handle the massive data load. But generating a single static frame of the future is one thing. To be a true world model, this AI has to generate seamless video.
Right, it needs flow.
It has to deeply understand time. I mean, if I'm driving, the car ahead of me can't just flicker in and out of existence or teleport from frame to frame. How do they enforce the laws of physics across time without breaking the system?
Enforcing that consistency is traditionally a massive headache in video generation. Usually engineers use a technique called backpropagation through time, or BPTT.
I've heard of that. It's heavy.
It is incredibly heavy because flow matching is an iterative process, taking many tiny mathematical steps to gradually turn noise into an image. BPTT requires you to unroll that entire integration trajectory step by step to calculate your error.
Right.
And then you have to backpropagate your corrections backward through every single one of those tiny steps across multiple frames.
Here's where it gets really interesting for me, because computationally, that sounds like a total nightmare. To me, BPTT is like trying to map out a cross-country road trip by calculating the exact physics, friction, and rotation of every single tire rotation along the entire highway.
That is a very accurate way to picture it.
It is just way too much data. You're going to run out of memory, or the math is just going to fall apart.
And the math absolutely falls apart. You experience what is known as vanishing gradients.
Right, where the signal just gets lost.
Exactly. The learning signal fades away into nothing because the mathematical chain is just too long and complex. So the innovation in FlowWM is a brilliant workaround they call the differentiable one-step projection.
I'm guessing that means they aren't unrolling the whole timeline. How do they shortcut it?
Well, instead of integrating the whole flow step by step to see where it ends up, the model looks at its current noisy state, evaluates the velocity vector it's currently pointing toward, and just draws a straight linear projection right to the estimated final endpoint.
Really? Just a straight line?
Yeah, it basically says, based on my current trajectory and speed, here is exactly where I mathematically estimate I will end up.
So they literally skip calculating all the individual tire rotations and just point a straight line to the destination on the map.
A perfect analogy. And because they can estimate that final destination in one single differentiable mathematical step, it unlocks two massive benefits for training the AI.
Okay, what's the first word?
The first is temporal consistency loss. They can apply physics-informed constraints directly on this estimated endpoint to ensure that the time derivatives, meaning the way objects accelerate or move from frame A to frame B, actually match real-world dynamics.
Wow, so it forces the model to respect momentum and object permanence without ever having to unroll the whole agonizing timeline.
Exactly. It's highly efficient.
That is incredibly elegant. It saves memory while still enforcing physics. And the second benefit, I imagine it has to do with how the system is evaluated, maybe?
It does. The second benefit revolves around task-driven objectives. Because they're generating these high-dimensional Dyno V3 features directly, they can actually plug in a frozen, pre-trained object detector right into the training process.
Wait, they test it while it's training?
Yes, they take that one-step projected endpoint, feed it to the object detector, and calculate exactly how well the detector can spot cars and pedestrians in that imagined future. Then, they backpropagate that detection loss only through that single projection.
Let me make sure I'm grasping the magnitude of that. The AI isn't just learning to make a future that looks plausible to human eyes, right? It is actively optimizing its own generated reality to be maximally useful for the specific downstream task of object detection.
That's it entirely.
It's learning to generate futures that are explicitly easier for a car's safety system to see.
It creates a fully closed-loop system where the world model and the perception system are perfectly aligned.
Man, that is smart. This raises an important question, though. We've covered a lot of theory. The wide heads, the time step shifts, the one-step projections. I mean, it all sounds incredible on a whiteboard.
Sure, theory is one thing.
Right. But how do we know this AI actually understands the unpredictability of reality better than the older models? A theoretical ghost car is bad, but how do we measure the improvement in practice?
So to prove it out, the researchers ran FlowWM through two major benchmarks. The first was a highly controlled synthetic environment called bouncing shapes. Imagine a 2D box with two objects, like a red square and a blue ball, bouncing around inside it.
Sounds like an old DVD logo screensaver.
Very similar setup. But they added a critical twist to introduce chaos. Every time an object hits a wall in this box, it has a 50% chance of bouncing normally based on standard physics, and a 50% chance of reversing its velocity entirely.
Okay. So every single collision creates a fork in the road.
Yes.
You get an exponentially branching tree of possible futures very quickly, which is exactly the unpredictability a world model needs to handle.
Precisely. And because it's a synthetic benchmark, the researchers could perfectly calculate every single valid future mathematically. That allows for rigorous testing of precision and recall.
And how did FlowWM do?
It absolutely shattered the competition here. They measure this using an F1 error rate, which is a metric that balances precision and recall, where a lower score is better, of course.
Right, lower is better.
The prior state-of-the-art stochastic model, from a team led by Walker, had an F1 error of 14.4. The deterministic model, DynoWM, the one which hallucinates those average ghost futures, scored a 17.8.
Okay, 14.4 and 17.8. And FlowWM?
FlowWM achieved an F1 error of 4.31.
Wow, wait, let's translate that math for a second. Going from an error rate of 17.8 down to 4.31 isn't just a marginal tweak. In practical terms, it means the older models were hallucinating impossible physics or ghost objects 3 to 4 times as often as FlowWM.
It is a completely different league of accuracy.
It really is. But, I mean, bouncing shapes in a 2D box is still synthetic. What happens when you put this on a real street?
And that brings us to the ultimate test. Their second benchmark, called future perception, which they derived from the Waymo open dataset.
Okay, Waymo. So this is real-world autonomous driving data captured from actual vehicles?
Yes, we are talking high-resolution 1920 by 1280 video. It features extremely complex dynamics, partial observability, where things are hidden behind other objects, pedestrians, cyclists, occlusions, the works.
Sounds messy.
It is. The task was brutal. Give the AI just 4 context frames from the past and ask it to accurately predict the next 12 frames, which translates to 1.2 seconds of future driving.
In highway driving, 1.2 seconds is an eternity. A vehicle can change lanes, a pedestrian can step out, a light can change. There's massive uncertainty. How did FlowWM perform?
It achieved state-of-the-art performance across the board. They measured downstream object detection accuracy using a metric called APL, average precision loss, where a lower score means the system is far better at accurately drawing bounding boxes around objects.
Yep.
They also measured depth estimation, how well the AI understands the 3D geometry of the scene, using RMSE or root mean square error. Across both these metrics, FlowWM significantly outperformed both the deterministic predictors and the VAE-based models like 1.2.2.
So it definitively beat the blurry mean, and it avoided the pixel trap.
It did.
But I am curious if the researchers tried to level the playing field at all. Like, could they just fix the VAE models by upscaling them somehow?
What's fascinating here is that they tried exactly that. They attempted to cheat the system to help the VAE model out. The researchers thought, okay, the VAE model struggles because it's compressed latent space, lacks semantic detail. What if we take the VAE's future predictions, decode them completely into standard pixels, and then re-encode those pixels into the high-dimensional DIO-V3 space before we run the object detector?
Oh, like trying to upsample a heavily compressed, blurry JPEG by putting it through a fancy high-definition filter. I'm guessing you can't invent data that isn't there. Did it work?
It actively hurt the performance.
Really? It got worse.
Yes. The object detection score dropped. The APL got worse, moving from 17.5 down to 16.5. This was a massive aha moment for the team. It definitively proves that if the semantic, structural information is lost during that initial low-dimensional prediction stage, it is gone forever.
Wow.
No amount of post-processing or clever re-encoding can magically bring it back. You have to preserve the high-dimensional details from the very beginning, which is exactly the gap FlowWM bridges.
That's incredible. I want to synthesize all this regarding the prediction horizon, though. So what does this all mean for long-term prediction? If the car has to guess 12 frames out and the uncertainty of the world keeps compounding with every single frame, doesn't the AI eventually just get completely confused and lose track of reality?
Well, if we connect this to the bigger picture, you have to look at Figure 6 in the paper. It tracks latent error over the entire prediction horizon. For deterministic models, the error rapidly spikes as time goes on.
Because it's constantly averaging diverging futures.
Exactly. The further out it guesses, the blurrier and more mathematically invalid the prediction becomes. It strays completely off the manifold of reality until it's just producing noise. But FlowWM degrades much, much slower.
Because it's not averaging the chaos. It's using flow matching to pick a valid, mathematically sound universe and sticking to it.
It maintains distinct, physically valid hypotheses. Even if the specific future it generated doesn't perfectly match what actually happened in the real-world ground truth video, the future it did generate is structurally sound.
The vehicles have edges, the pedestrians have volume.
Exactly, which means the downstream object detectors can still confidently identify the hazards within that generated future, keeping the system safe.
Okay, let's bring this all home for you listening. The core aha moment of this deep dive is this. To build a robust AI world model that can actually survive in the real world, you just cannot compromise. You absolutely need stochastic modeling to handle life's inherent unpredictability. You can't just average out the chaos into ghost cars. But you equally need high-dimensional semantic representations so the AI actually knows what it's looking at, preserving the rigid geometry of the world rather than just focusing on pretty pixels.
And as autonomous agents, whether they're self-driving cars on our highways or physical robots navigating our homes and workplaces, as they become increasingly integrated into our daily lives, this dual capability is non-negotiable.
Yeah, it really is.
It is the architectural foundation that will prevent a machine from making a catastrophic error when faced with something utterly unexpected.
Like a pedestrian stepping off a curb unexpectedly, or our squirrel darting into the road. The machine has to be able to see the branching paths of reality with perfect clarity.
Because without that clarity, the system is fundamentally unsafe.
It leaves you with a rather profound thought, kind of stepping outside the complex math of flow matching and wide heads for a moment. If an AI can now accurately hold multiple, high-dimensional, equally valid futures in its mind simultaneously to navigate the world, does that mean the key to artificial intelligence isn't just learning from the past, but achieving the capacity to literally daydream 1,000 tomorrows all at once?
It's a staggering thought.
And if they are generating physical futures that complex and that detailed, calculating velocity and depth perfectly, how long until their simulated worlds are indistinguishable from the real one?
Something to think about for sure.
Definitely. Next time you're driving and you see that squirrel freeze on the edge of the asphalt, remember your brain is effortlessly splitting the universe to keep you safe. And now the machines are finally learning how to do the exact same thing. Thanks for joining us on this deep dive. We'll catch you next time.